what we're going to cover today, angles and arcs. And again, some of this is going to be going back over some stuff that we went over previously. Fill in what you need to fill in on this slide. Hopefully I won't go too fast on this. We talked about central angles before. Anytime you have a central angle, what a central angle is in relationship to a circle, you have the center point of the circle. Central angle always has its vertex at the center of the circle. Notice that this central angle, the sides of the angle are 2 radii, so they're always going to be congruent to each other. That's something that we're going to use down the road. And then every angle that we deal with cuts off part of the circle, cuts off an arc. That arc and that angle go together, and some of them have different relationships, and we'll talk about that as we go on throughout dealing with circles. For a central angle, if the vertex is at the center, then the angle and the arc are the same. When you measure arcs, arcs are measured just like angles are measured in degrees, or they could be measured in radians, and that's something we haven't talked about, and we're going to talk about it today. So if this angle is 52 degrees, then that means this arc right here has to be 52 degrees. So central angles are pretty easy. Vertex at the center, the angle and the arc are the same. Please also remember that circles are always 360 degrees. Dealing with arcs, or talking about arcs, fill in what you need to fill in on this. A minor arc is an arc that's less than 180 degrees, so less than half a circle. Whenever you name a minor arc, you name it with 2 letters. This is your arc going around here. So a minor arc, we just name it just like we would a segment with 2 letters, so PQ, but the symbol, instead of a segment symbol, it's this arc symbol. So it's an arc symbol. It's supposed to be something about like that. A major arc, should have been point R here on my PowerPoint, there wasn't. A major arc is more than 180 degrees. So when you name a major arc, you have to use 3 letters, because if we just said arc PQ and we meant to go around this way around the circle for that major arc, nobody would understand that. They would just go the shortest path for P to Q and go that route. So we have to put in a 3rd letter. And we just like we're going around the circle. So if we're starting at P and going this way, to name that arc, then it's arc. It's still got that arc symbol. First letter P, then we could go through R, and then we get to Q. You only need 3 letters just to show which direction you're going around the circle. So 2 letters to name a minor arc, which is less than 180. 3 letters to name a major arc, which is more than 180. A semicircle, or what's considered half a circle, when you take a diameter and draw a diameter in a circle, you split the circle in half. This arc is a semicircle. The other arc going around this way is also a semicircle. And a semicircle is always 180 degrees. We talked a little bit about semicircles. Remember, if you draw, last time we dealt with this, if you draw an angle inscribed in that semicircle, something like that, that angle is always going to be a right angle. And that triangle would be a right triangle then, and we could use Pythagorean's theorem, SOHCAHTOA, and all that other stuff. Arc length. This is something that we sort of went over. We just went over it quickly. To find arc length, and this book uses that lowercase l to stand for arc length. So they use that. So if you see that, that's what it's talking about, is the length there. Arc length, the length of this arc. If I start walking here at N and I walk to T, that length, notice it's curved, so we can't just measure it like we would a segment or something. So with that curve, what we do is we take the arc measure, so whatever the measure of this arc is, maybe it's 100 degrees or whatever that measure of that certain arc is, divided by 360 times the diameter of the circle, and then times pi. Don't make this problem or this formula any harder than it is. Let's say they tell us the radius of the circle is 5 centimeters. Then all you're going to do to find the arc length is, we know that this arc measure is 100 degrees, so that goes on top, 360 on bottom, times, if the radius is 5, then that means the diameter has to be double that, which is 10, times pi, and you just grab your calculator and do the math. So you do 100 divided by 360, then times 10 times pi, and that's going to tell you the length in centimeters, inches, whatever it happens to be. In this case, it happens to be centimeters. So that's going to tell you, if you walk from this point to this point, how many centimeters you would walk. Radians, this is new. We haven't talked about radians. We're going to talk about them right now. Fill in what you need to fill in on this. Give you just a second. Radians are just another way to measure angle. Radians actually measure angular movement. So it's sort of like degrees, just a little different, a different way to write it, and it's used for different things. This little symbol here looks like this, and it's got a little sort of tilde in it. So it's just an O with a tilde in it, and that's a theta. And that's used to talk about angles a lot. So that's used to as like the variable for an angle when you don't know an angle. So if you see that, you're probably dealing with angles. When the radian measure of a central angle is theta equals arc length, which again, this book uses L, divided by the radius. So all radians do is they compare the length of the arc to the radius of the circle. 1 radian is 180 degrees over pi. The main things to remember here on this slide are how to convert it. So if we're going from degrees to radians, all you do is you take your degrees number, whatever that is, and you multiply it by pi over 180. And if you're going from radians to degrees, then you multiply by 180 over pi. So nothing really hard about this. You're going to use your calculators a lot. But sometimes when you want things in radians, your radian answer is going to look something like this. That's going to be the measure of the angle, but that's in radians. So it's more like when we're dealing with radians, we're trying to give a more exact answer rather than rounding everything off to the nearest degree or whatever. A couple of examples here. Write 135 degrees in radians. So we want to change this 135 degrees. We want to convert it from degrees to radians. Do these examples there in your notes as I do them. If we're going from degrees to radians, let's go back for just a second. Degrees to radians, we're going to multiply by pi over 180. So we just take 135 and we times it by pi over 180. Now again, if we're writing things in radians, we probably don't want to just grab our calculator and give the decimal answer. Sometimes you may, but here what we're going to do, you just multiply this number times the top, which is pi, so you get 135 pi over 180. If you grab your calculator, and on your calculator you either got that ND button or you got the ABC button or whatever it is, however you can reduce a fraction on your calculator, we're going to use it. So get your calculators out, and all you're going to do on your calculator, you're going to put in 135, and then the ABC button or the ND button or whatever button it is, and then 180. And it's going to reduce it as a fraction for you. So I got my calculator and I put in 135 and I hit the ABC button, 180, and it tells me 3 over 4. So it's what happens, the way you write this, the 3 stays on top, the pi also stays on top, so 3 pi over 4 radians. That's what your angle measure is. So 135 degree angle is the same as 3 pi over 4 radians. Just two different ways to write it. If we're going the other way, we take our radians measure. This time it's 11 pi over 6. And we're going to times it by, if I go back to this, we're going to times it by 180 over pi to go from radians to degrees. The first thing I hope you notice here is you got a pi on the bottom. If we multiply this, if I just write it out, this is 11 pi times 180 on top, and 6 times pi on bottom. Well, we got a pi on top and we got a pi on bottom. They're just going to cancel each other out. Now we grab our calculator and we just do what's on top, 11 times 180. And that gives me 1980. And we still got the 6 on bottom, so we're going to divide that. So 1980 divided by 6. And this time it comes out even, and it comes out to 330 degrees. Now, you got to remember 330 degrees, you're saying, well, that's bigger than 180. We've never dealt with angles like that. We're on a circle now. So what we're doing is we're saying if we started here on this circle, we went around the circle 330 degrees, maybe somewhere to like right there. So we're going to have angles larger than 180 now when we're dealing with these circles. So that's how to convert from degrees to radians and radians to degrees. Again, use your calculator, don't make that any harder than it really is. Next example, find the length of arc. I know this is sort of ugly, but that says arc ZY. So we want to find the length of arc ZY. We want to find, if we start walking from Z right here and walk to Y, how many centimeters would we walk? Well, there's several different ways we can do this. One of the ways is we got this angle here, and it's in radians. We could change that to degrees, and since it's a central angle, that's going to be the same as here, and we use that arc length equals, if we go back in our notes, the arc length equals the arc measure over 360 times diameter times pi. We could use that formula. We could also, if I go back, let's go back and look at this. There it is. We got arc length over radius. We could also use that as part of it. And it might be easier to use that to just know what our angle is and what the radius is, and then switch it up to find the arc length. It doesn't matter to me. I'll do it both ways here in a second, just to let you see how the two different ways work. And you decide which one you want to use. It makes no difference to me. They should both come out the same. So the first thing here, I'm going to change this. If I'm going to use this formula, I'm going to change this into degrees. And it's 3 pi over 4. Well, we just got done doing that, I think. 3 pi over 4 was 135 degrees. To change that, same idea. If I go back here, to change it from radians to degrees, we multiply by 180 over pi. So if we didn't already, if we hadn't already have done that one, then we just do that to change it. So 3 pi over 4 times 180 over pi. Again, that's 3 times pi times 180 on top over 4 times pi on bottom. The pi's cancel out. On top, just grab your calculator. 3 times 180 is 540. You still got divided by 4 on bottom. 540 divided by 4 is 135. So that means this angle is 135 degrees. If that angle is 135 degrees, it's a central angle. So that means this arc has to be 135 degrees. And then if we want to find the arc length here, we know the arc measure now is 135 divided by 360 times, we need the diameter. Well, they tell us the radius is 9 centimeters, so all the way across the circle is going to have to be 18 centimeters. So diameter is 18 times pi. And we just plug this into our calculator. 135 divided by 360 equals, and then times 18, then times pi. And I get that the arc length is about 21.21. We'll go out to the hundredths place since that's what we've been doing, and our units are centimeters. Now, if we use the other formula, we had theta equals arc length over the radius we should get the same answer. Theta, this time if we use the radians, that's 3 pi over 4 equals arc length. We don't know what the arc length is, so I'm just going to use L for our variable. And the radius is 9. We cross multiply. Since we have a proportion here, we can just cross multiply to solve this. 4 times L is 4L. We cross multiply this way. 9 times 3 pi, you just multiply the 9 and the 3, and you get 27 pi. I'm going to leave this in terms of pi for right now, because all we're going to do next is divide by 4. These cancel out and leave you with just L. And you can do all of this on your calculator. 27 times pi, then hit equals, then divided by 4, and I get 21.2, that's a point there, 0.21, and our units are centimeters. So either way, basically the same thing. This method is probably a little easier if they give you the angle in degrees, or the arc measure in degrees. And this method is probably a little easier if they give it to you in radians. But it's up to you. You can use either one you want. The only bad thing with this one, if it's in radians to start with, you need to change it like we did up here into degrees to find that arc measure. So this one, I'm just going to use that second method this time. Arc length over the radius and the reason I'm using this is because they give us our angle here in radians. So that angle, which is going to be the same as this arc, because it's a central angle, 7 pi over 12. That's what goes in place of theta right here. The arc length we don't know, so that's our variable, that's our L. The radius this time is just 2. We cross multiply. We get 12 times L equals 2 times 7 pi. You just multiply the 2 and the 7, and you get 14 pi. To solve for L, we divide both sides by 12. These cancel out. You're left with L equals, and then you just grab your calculator. 14 times pi, it equals, and then divided by 12, and I end up with about 3.67. And our units, since our units here were inches, these are inches. So that's the length. If I start walking at M, and I walk till I get to N, I'm going to walk about 3.67 inches. Next thing, inscribed angles. We talked about inscribed angles. Remember, an inscribed angle, vertex is on the circle. So the vertex is on the circle and the angle goes in here. Notice it still cuts off a certain arc. The difference this time from a central angle, vertex is at the center, the angle and the arc are always going to be the same measure, same degrees. For an inscribed angle, the angle measure is half the arc, or 2 times the angle equals the arc. So if I tell you that this angle is 50 degrees, then that means this arc out here is going to be 100 degrees. And we talked about inscribed angles before. Those are the 2 easy ones, central angles and inscribed angles. Central angle and the arc are the same. Inscribed angle, the angle is half whatever the arc is, or the arc is double whatever the angle is, however, whichever way you want to say it. We dealt with this one. If a quadrilateral is inscribed in a circle, remember, to be inscribed, all the corners have to be on the circle. So if it's inscribed that way, opposite angles are supplementary. That means opposite angles have to add up to 180 degrees. So these 2 angles add up to 180, and those 2 angles have to add up to 180. They're not congruent. Opposite angles have to add up to 180 degrees. And we talked about this one already. If a triangle or an angle is inscribed in a semicircle, so if we have this diameter and it's inscribed, or we inscribe an angle here with the same endpoints as that diameter, that angle must always be 90 degrees. So then it forms a right triangle, and we can use all the stuff that we have, Pythagorean's theorem, SOHCAHTOA, and all that stuff to help us find missing parts. And the last thing here, I think this is the last thing. If 2 angles are inscribed in a circle intercept the same arc or congruent arcs, then the angles have to be congruent. So if I do this, I draw that angle. So I have this angle right here, angle NTH. Notice the arc that it cuts off of the circle is arc NH. And then if I draw another angle, or angle NSH, notice the arc that it cuts off is this arc right here, which is arc NH. They cut off the same arc. So they both go with that same arc. Well, what that tells us is if they both go with that same arc, then these 2 angles have to be the same, because they're both inscribed angles. So those 2 angles have to be the same. So anytime I have a circle and I draw an angle and it cuts off this arc, then I draw some other angle and it cuts off that same arc, these 2 angles have to be congruent to each other. All right, the assignment, we're going to talk about this and we'll see how it goes in class. For now, we're just going to start with this. So open up your books to page 583. We're going to try to work on some of this during class and work on it together, and we'll decide how to do that. Then this second page, we'll make a decision on it as class goes along. We may hold off on this page and do it next time.